Hello there, and welcome back to another exciting episode of Linear Algebra. I think I said that last video. So this is section 1.8, lecture number 2. Here we're just going to go over an example, sort of more ideas for ways we can use the tools that we already have to continue to study matrices as, instead of sort of collections of vectors, maybe as these transformations which can map vectors in a space to vectors in another space, right? So what we learned is an M by N matrix maps vectors in Rn to vectors in Rm. And so here A is a 3 by 3 matrix, so we don't have to worry too much about organizing the indices, thankfully. We know that A can be a linear transformation that maps R3 to R3. So I just want to go over a couple different types of questions you might see regarding this, talk about how we can solve them, and then we'll learn some interesting facts about linear transformations. We'll actually get to do our first, we've maybe done a proof or two already, but we'll get to do a couple fun proofs. So here we go. We've got this matrix A, like it says on the board. We've got this transformation mapping R3 to R3. Defined by T sub A of x is equal to A times x. Standard from what we saw last time. Question A, I just wanted to sort of go back over the definition. We want to find the image of this vector x. So remember, the image of x is just equal to T of x, which is just equal to A times x. So here, the solution to part A, well, the image of x is just equal to, again, A times x, which is the matrix 1, 4, 3, negative 9, negative 3, 1, 2, 6, times the vector x. Ooh, now I get to do some multiplication. And so notice here we should get a vector of length 3, given how we've defined our linear transformation, given that we know the dimensions of A. We're going to do the vector multiplication dance 3 times. All right, so first entry I get 3. Then I think I get 0. And then I get 12. And so notice this is equal to 3, 0, 12. And so this vector, in fact, is the image of x. The vector 3, 0, 12 is the image of the vector 1, 0, 2. All right, so that one was straightforward enough. Now I want to ask a slightly different question. And this is a very good question, sort of bringing together a lot of what we've learned. Part B, what we want to do is find all vectors in R3 that are mapped to the 0 vector. And so again, this type of question will ask us to sort of recall our knowledge of matrix vector multiplication, matrix equations, because remember, anytime we're talking about a linear transformation, at least at the moment, we're actually just talking about matrix multiplication, but in the context of mapping vectors of one space to another space. And so what this question is asking us to do in reality is solve the matrix equation AX equals 0, where here this is our matrix A. Because notice, if A times X equals 0, then by definition of our linear transformation, X is mapped to 0. And so to solve this, we just want to set up an augmented matrix and row reduce. And so notice, again, I'm going to leave off the last row of zeros here because I can determine what the solution to this is without needing the last row of zeros. Once I've read everything out, we can sort of correspond this to zeros. And much like before, I will include full details of how I did the row reduction in the solutions guide to the corresponding worksheet. But for now, I'll just say we row reduced this matrix. So row reduce there's not too many steps, but after row reducing, I get the following RREF matrix. And so this corresponds to the following system. Remember, x1 minus 5x3 equals 0, and x2 plus 2x3 equals 0. And so specifically notice that x3 is a free variable here. And so what that means is that we can express our solution in parametric vector form to this equation. And so here's sort of why we introduced, or one reason we introduced parametric vector form back in section 1.5, 6, section 1. Whatever section we introduced it in. Why we, 1.5, it was 1.5, I remember now. Because, notice, the parametric vector form for the solution, well, remember we can describe what all solution vectors look like. So we'll let x3 equal this free variable t. And if I solve for each other variable in terms of x3, I get the following solution in parametric vector form. And that is, every single solution to this homogeneous equation must be a scalar multiple of this vector 5, negative 2, 1. But in particular, notice that we've actually just answered this question, right? That is all x, all vectors that are mapped to the 0 vector. Well, they're all vectors which give a solution to this homogeneous equation, which we've just determined are all vectors that are scalar multiples of this vector here. And here's a different color marker. So that would be our solution to question B. This would describe all vectors that are mapped to 0. You could alternatively say it's the span of this vector, that is all scalar multiples of that vector. Or you could express it like this. All right, so again, how we can sort of talk about linear transformations and use our previous knowledge of matrices to answer questions concerning linear transformations. All right, so I want to go over a couple facts about linear transformations, and I'll actually prove them because the proofs are very short and sort of nifty because they use a lot of properties that we already have. And then we'll do one more example, and then for now, we will be done. So, number one is that, well, so first off, if T is a linear transformation. And so, in particular here, notice that we're just sort of assuming the broad case that T is a linear transformation. So this is true of every linear transformation. And what we'll eventually see is we can actually expand this to not just linear transformations associated with matrices, although for now we're mostly, I think, only pretty much talking about this in terms of matrices. But so, no matter what linear transformation we're working with, T should always map the 0 vector to the 0 vector. So that is, take the 0 vector in our domain, it should always map to the 0 vector in our codomain. So why is that? Well, this is sort of a very nifty proof that this always has to happen, I think. Because it almost feels like it's, again, one of those things that's sort of cheating the system. But remember, well, so the way I'm going to do this, so t of the zero vector, I can actually rewrite like this, where here this is t of the number 0, so just a scalar, times any vector u, right? And these two things are definitely equal because 0 times any vector u is just the 0 vector. Well, we know that for all linear transformations, I can actually factor scalars out. Right? And this is one of the properties of linear transformations that we've just defined. Well, and so now this is a vector in my codomain, right? T of u is a vector that lives in the codomain. But I'm multiplying it by the scalar 0, and so this in fact just equals the 0 vector. There are actually, I think, a lot of ways to prove this fact. Here, this is just one specific way to do it. But this is a very important fact to remember, that t of the 0 vector is always equal to the 0 vector. And of course, if you think about it in terms of matrix multiplication, it's definitely always true because, right, a times the 0 vector is just always 0. But we can actually prove this just using the properties of a linear transformation, not even necessarily thinking about it with matrices. So we also know that if I have two scalars and two vectors, that this t of c times u plus d times v is equal to c times t of u plus d times t of v. And so the proof here just sort of takes this and breaks everything down in the way that you think it should. So we can give a few intermediate steps here. So remember, I can split this up across sums. And then I can factor out scalars. And so really all this proof does is it just sort of uses the facts that we have about linear transformations to take one side of the equation and work it down to the other side. But both of these facts are important to remember because they allow us to work with linear transformations in very nice ways. And as we'll see in this last example here, that they actually allow us to learn a lot about linear transformations we might have previously had not a lot of information. And actually your book has, so here, I'll read you this in your book. It says, this principle in particular is referred to as the superposition principle. And I actually don't know a whole lot, or know enough about physics or engineering to say a whole lot more than that, but if you're into physics or engineering, this is the superposition principle. All right, so I want to do one last fun example using these two properties. And I highly encourage you, before I go through the solution of this, to pause the video and try and work through this on your own, because I think this is a really fun and rewarding thing to work through and sort of figure out. But so, let t, so we have this linear transformation which maps R2 to R2. But the catch here is that I'm not going to give you the matrix. And so So we're given that t maps this vector u into the vector 2, 1, and maps the vector v into the vector negative 1, 3. But we don't have the matrix, and we want to find the image of this vector 3u plus 2v. So how do we do it? So like I said, pause the video here, try it for yourself, think about it a little bit, and then I will go over the solution. All right, so to do this, we're actually going to have to use the principles of linear transformations that I just introduced. So notice here I've got t of 3u plus 2v. And so what we don't want to do, interestingly enough, is actually calculate 3u plus 2v. So we know nothing about that exact vector when we look at it in this way. And as we'll see, a lot of math is just sort of like trying to turn things into a problem that we know how to solve. We don't know how to solve this problem, but we have some rules which can maybe turn this problem into the sum of two problems which we know how to solve. So by the vector rules introduced, notice this is equal to 3 times t of u plus 2 times t of v. And we know t of u and t of v. So this is equal to 3 times 2, 1 plus 2 times negative 1, 3. And so if I do this, I get 6 minus 2 is 4, and 3 plus 6 is 9. And so notice, knowing nothing about the linear transformation, we can actually use just the knowledge of two vectors to know exactly how the linear transformation works. And so something interesting to think about, I think in this case, notice u and v, well, it's not super obvious, I guess, looking at it, but the span of u and v, right? So if you think about all linear combinations of u and v, we have the ability to calculate the image of any vector that can be written as a linear combination of u and v, right? Just knowing where u goes and where v goes, as we saw here. Because this was a vector that is a linear combination of the two, and we actually know where that vector went. And so in fact, u and v span R2. That's a fact that can be shown through some matrix we're reducing. But this means that just knowing the images of u and v, I actually know the image of every single vector in R2 without even needing to know a matrix or anything else, that I can define the entire linear transformation just by knowing two vectors. So keep that idea in mind, because I think that will be important quite a bit through this course and maybe later on. So anyways, that wraps up this video, and I'll see you next time.